Ask anyone which planet in our solar system is the most dangerous, and the answer comes back almost instantly. Jupiter. The largest, the loudest, the most violent storm system ever recorded. A magnetic field so powerful it could fry a spacecraft before it even arrived. Jupiter wins by instinct. But instinct is wrong. Saturn. The planet people hang on their walls. The one children draw with crayons. The golden world wrapped in rings so beautiful they defined an entire era of astronomy, may actually be more dangerous than Jupiter in ways that matter most. Not because it is bigger, not because it is louder, but because everything about Saturn's appearance is a lie. And once you understand what is actually happening beneath those golden clouds, you will never look at it the same way again. If you enjoy science that challenges what you thought you knew, take a second to like and subscribe. It helps more than you think, and we never take it for granted. Now, are you comfortable? Let's begin. If you stopped 1,000 people on the street and asked them one simple question, which planet in our solar system is the most dangerous, 900 of them would say Jupiter without hesitation. The other 100 might say Venus or the Sun, depending on how literally they took the question. Almost nobody would say Saturn. And that answer, that instinctive, automatic, nearly universal answer, tells you something fascinating. Not about Jupiter, about how human beings judge danger. We look for size. We look for noise. We look for the thing that appears the most aggressive, the most obviously threatening, the most visually violent. And Jupiter delivers on every single one of those expectations so completely that it has dominated the public imagination as the solar system's ultimate monster for as long as people have been pointing telescopes at the sky. Let us be honest about why. Jupiter has earned its reputation. It deserves a significant amount of the fear people attach to it. This is not a planet you underestimate casually. It is the largest planet in the solar system by such an absurd margin that every other planet could fit inside it, all of them, combined. You could pour Earth into Jupiter more than 1,300 times and still have room left over. When you look at a scale model of the solar system and see Jupiter next to Earth, the comparison does not feel like two planets from the same star. It feels like a bowling ball next to a marble. The difference is so extreme, it warps your perception of everything else around it. And the size is not just cosmetic. Jupiter's mass drives everything about its behavior. It is 2.5 times more massive than all other planets in the solar system combined. That mass generates gravitational pull strong enough to steer asteroids, redirect comets, and warp the orbits of nearby moons with tidal forces that can tear a world apart from the inside. Io, the innermost of Jupiter's 4 large Galilean moons, is the most volcanically active body in the entire solar system. Not because of anything happening inside Io, but because Jupiter's gravity is flexing the moon's interior like a stress ball, generating so much internal friction that the surface erupts constantly. Hundreds of active volcanoes, rivers of sulfur, a landscape so tortured that the surface completely replaces itself every few million years. That is what Jupiter does to objects near it, not through collision, not through radiation, although that is coming, through gravity alone. Then there is the atmosphere. Jupiter's Great Red Spot is the single most famous storm in the solar system. It is a high-pressure anticyclonic system that has been continuously observed for at least 190 years, with possible earlier sightings stretching back to the 17th century. When astronomers first documented it in the 17th century, it was already enormous. At its peak size, the storm could have swallowed 2 or 3 Earths side by side. Winds at its edges reach speeds of roughly 270 miles per hour. The internal dynamics of the storm involve updrafts and downdrafts, cycling material through a vertical range of more than 60 miles. It is not just a surface feature. It is a 3-dimensional vortex system embedded in the atmosphere, drawing energy from the surrounding cloud bands and sustaining itself through mechanisms that scientists are still working to fully understand. The Great Red Spot is so iconic, so visually dramatic, that it has become a kind of logo for planetary danger itself. When people think of hostile weather on another world, this is what they picture: red, swirling, immense. But the storm is only part of Jupiter's atmospheric hostility. The entire planet is wrapped in bands of counter-rotating jet streams that produce turbulence at a scale Earth has no equivalent for. White oval storms the size of terrestrial continents appear, merge, and dissipate across decades. Lightning bolts have been detected in Jupiter's atmosphere that release energies thousands of times greater than any lightning strike on Earth. The Juno spacecraft, which has been orbiting Jupiter since 2016, detected shallow lightning near the poles and deep lightning near the equator, revealing that Jupiter's atmospheric electrical activity extends across a vertical range far larger than any planetary atmosphere previously studied. The clouds themselves are layered: ammonia ice on top, ammonium hydrosulfide beneath, and water clouds at the deepest visible level. Below that, the atmosphere does not end, it just keeps going, deeper, denser, hotter. There is no surface. There is only a gradient of increasing pressure that eventually crosses the threshold, where hydrogen gas becomes a liquid and then continues further until the hydrogen is compressed into a state so dense and electrically conductive that it behaves like a metal. And then there is the radiation. This is where Jupiter crosses from impressive to genuinely terrifying. Jupiter has the most powerful magnetic field of any planet in the solar system. Its magnetosphere is the largest structure in the solar system, apart from the heliosphere itself. If you could see it with your eyes, it would appear larger than the full moon in Earth's sky, even though Jupiter is hundreds of millions of miles farther away. That magnetic field traps charged particles from the solar wind and from Io's volcanic emissions, creating radiation belts so intense that they would kill an unprotected human in minutes. Not hours, not days. Minutes. The radiation dose near Jupiter's cloud tops exceeds several thousand times the lethal threshold for a human being. The Juno spacecraft was specifically designed with a radiation vault, a titanium-walled compartment protecting its most sensitive electronics, because the engineers knew that without it, the instruments would be destroyed within weeks. Even with that protection, Juno's systems accumulate radiation damage with every orbit. When the Galileo spacecraft was deliberately crashed into Jupiter's atmosphere in 2003, the decision was made partly because the radiation had degraded its instruments to the point where continued operation was becoming unreliable, and partly because NASA wanted to ensure the spacecraft would not accidentally contaminate Europa, a moon suspected of harboring a subsurface ocean. The radiation at Europa's orbit is already severe. A human standing on Europa's surface without protection would receive a lethal dose within a single day. So when people say Jupiter is the most dangerous planet, they are not speaking from ignorance. They are responding to a real and extensive catalogue of genuinely lethal characteristics: size, gravity, atmospheric violence, radiation, magnetic field intensity. Jupiter delivers on every front with a kind of overwhelming, obvious, in-your-face hostility that leaves very little room for argument. Except there is room for argument. And the argument begins with a question that almost nobody thinks to ask. What if the most dangerous planet in the solar system is not the one that looks the most dangerous? What if danger in space does not always announce itself with red storms and crushing radiation belts? What if the most hostile world is the one you never thought to fear because it looked too beautiful, too elegant, too calm to possibly hurt you? That is where Saturn enters the conversation. and it enters quietly, almost politely, which is exactly the problem. Saturn is the second largest planet in the solar system. It is massive by any terrestrial standard, roughly 9 times the diameter of Earth, with a volume large enough to contain more than 760 Earths. It possesses a powerful magnetic field, a deep and complex atmosphere, a vast system of moons, and the most spectacular ring system of any planet ever observed. By every objective measure, Saturn is one of the most impressive objects in the solar system. And yet, when people think of Saturn, the first word that comes to mind is almost never dangerous. It is beautiful. It is that planet with the rings. It is the one that looks like a piece of cosmic jewelry, the one that children draw in art class, the one that appears on posters and desktop wallpapers and science fiction movie backdrops as the symbol of elegance and wonder. Saturn's visual identity is so thoroughly associated with beauty that it has become almost impossible to separate the planet from the aesthetic it projects. That separation is exactly what this story is about. Because the gap between what Saturn looks like and what Saturn actually is represents one of the most dramatic mismatches between appearance and reality anywhere in the known universe. And that mismatch is not an accident of perception. It is built into the physics of the planet itself. To understand why Saturn fools us, you have to understand how we receive information about planets. Almost everything we know about the appearance of worlds beyond Earth comes from reflected light. Sunlight hits a planet's atmosphere or surface, bounces back toward us, and our telescopes or eyes detect whatever wavelengths survive the journey. The colors we see, the textures, the brightness, the contrast between bands and spots and poles, all of it depends on what the atmosphere reflects and what it absorbs. Jupiter's atmosphere is visually loud. It reflects light in a way that emphasizes contrast. The cloud bands are sharply defined, alternating between dark belts and bright zones with clearly visible boundaries. The Great Red Spot sits like a wound in the southern hemisphere, its reddish-brown color standing out against the surrounding beige and white. Smaller storms, white ovals, dark barges, and turbulent wake regions dot the disk with obvious visual chaos. When you look at Jupiter through even a modest telescope, your eye immediately registers complexity and violence. The planet looks like a place where things are happening. Saturn does not look like that. Saturn's cloud bands are muted. The colors grade softly from pale gold near the equator to a gentle blue-gray at the poles. The transitions between zones are smooth. The overall palette is warm but restrained, and dominating everything, of course, are the rings. Those extraordinary, impossibly thin, stunningly bright rings that extend outward from the planet in a disk so geometrically perfect that when Galileo first saw them through his primitive telescope in 1610, he thought the planet had ears. He could not make sense of what he was seeing, because nothing in his experience prepared him for a structure that elegant. The rings are beautiful. That word is not an exaggeration. Multiple astronauts and planetary scientists have described Saturn's ring system as the single most visually stunning structure in the solar system. The Cassini spacecraft spent 13 years orbiting Saturn, and the images it returned are among the most breathtaking ever captured by a space probe. Sunlight filtering through the rings, the shadow of the rings falling across the cloud tops, the intricate structure of gaps and divisions within the ring plane, individual ringlets so thin they can only be resolved at close range. The visual experience of Saturn is so overwhelming that it dominates every other impression the planet makes. And that is exactly the trap, because while you are looking at the rings, while you are admiring the golden glow and the smooth cloud bands and the geometrically perfect disk of ice and rock encircling the planet, something else is happening beneath the surface. Something that the beauty distracts you from. Something that, if you could peel away the photogenic exterior and see the planet as it truly is, would make Jupiter look almost straightforward by comparison. But before we go beneath those clouds, we need to establish something critical, a framework, a vocabulary, because the word dangerous is doing an enormous amount of work in the title of this story, and if we do not define it precisely, the entire argument collapses into the kind of vague sensationalism that helps no one. When we say Saturn may be more dangerous than Jupiter, we do not mean that Saturn is bigger. It is not. We do not mean that Saturn has stronger radiation belts. It does not. We do not mean that Saturn wins in every single measurable category of physical hostility. That would be a false claim, and making it would require ignoring real data that clearly favors Jupiter in certain specific areas. What we mean is something more nuanced and, ultimately, more important. Danger is not a single number. It is not a scoreboard where you tally up points and declare a winner. Danger is context-dependent. It depends on what you are, where you are, what you are trying to do, and what you expect to encounter. A hidden crevasse in a glacier is more dangerous to a hiker than a visible cliff, not because the crevasse is deeper, but because the hiker does not know it is there. A calm-looking river with a powerful undertow is more dangerous to a swimmer than a visibly rough sea, because the rough sea warns you to stay out and the calm river invites you in. Saturn is the calm river. In the specific context of planetary exploration, atmospheric entry, long-duration proximity, and human or robotic survival, Saturn presents a set of hazards that are in several measurable categories equal to or greater than Jupiter's. Its wind speeds at the equator are significantly faster. Its atmospheric depth before reaching crushing pressures is greater, creating a longer and more disorienting descent with fewer reference points and fewer options for escape. Its storm systems, while less visually dramatic at the surface, operate with a geometric precision and a persistence that suggest atmospheric dynamics even more deeply entrenched than Jupiter's famous vortices. And its lower density, far from making it a gentler world, creates physical conditions that are in some ways more treacherous, precisely because they feel less immediately threatening. Everything about Saturn is designed, if you will forgive the word, to lull you, to make you feel as though you are approaching something manageable, something you have seen before, something that will behave the way you expect. It will not. Jupiter announces its danger at the front door. You know what you are getting into before you arrive. The radiation hits you first, far out from the cloud tops, like a warning shot fired across the bow. The magnetic field is so intense that your instruments start registering anomalies while you are still millions of miles away. The atmospheric turbulence is visible from orbit. The storm systems are mapped and catalogued and named. Jupiter gives you every possible signal that you are approaching a hostile world. Saturn gives you rings. Saturn gives you gold. Saturn gives you a planet so visually serene that the first instinct of every mission planner, every science communicator, every human being who has ever looked at it is to describe it in the language of wonder rather than the language of threat. And that instinct is the most dangerous thing about Saturn. Because when a planet this hostile is wrapped in an appearance this beautiful, the gap between expectation and reality becomes the primary hazard. You approach differently. You plan differently. You calibrate your instruments and your assumptions and your fear response for a world that is fundamentally not what it appears to be. That is not a metaphor. That is a statement about measurable physical properties that we are going to examine in detail, wind speeds that dwarf anything Jupiter produces at comparable latitudes. Storm systems so enormous and so stable that they challenge our models of atmospheric fluid dynamics. A pressure profile that traps you in a descent so gradual and so long that by the time you realize how deep you are, escape velocity is no longer achievable. And a magnetospheric environment that, while weaker than Jupiter's in raw intensity, interacts with the ring system and the moon system in ways that create hazards no other planet in the solar system replicates. Jupiter is a lion. You see the teeth, you hear the roar, you run. Saturn is something else, something that smiles at you, something that invites you closer, something that wraps itself in the most beautiful exterior the solar system has ever produced and waits for you to let your guard down. What follows will take apart that exterior piece by piece. We will start with what you see when you look at Saturn and end with what is actually there. The distance between those two things is where the real danger lives. There is a reason Cassini spent 13 years at Saturn, and the data it returned is still being analyzed more than 7 years after the mission ended. The planet was not what anyone expected. The atmosphere was more violent, the storms were more extreme, the internal dynamics were more complex, and the ring system, the beautiful, iconic, universally admired ring system, turned out to be something far stranger and far more hostile than a decorative feature of a peaceful world. Every new instrument that has been pointed at Saturn has returned the same verdict. This planet is not what it looks like. It is not what the golden glow suggests. It is not what the smooth cloud bands imply. It is not what the calm, stately orbit around the distant sun promises. It is something else entirely. And understanding what that something is requires doing the one thing that Saturn's appearance has prevented people from doing for 400 years. Looking past the beauty, looking beneath the rings, and asking the question that Jupiter's obvious violence has always made feel unnecessary. What is actually happening down there? The answer begins with wind. Wind on Earth is measured in miles per hour. A Category 5 hurricane, the most powerful classification in our system, requires sustained winds of at least 157 miles per hour. At that speed, well-built homes lose their roofs, trees snap like matchsticks, steel structures deform, cars become airborne. The damage is catastrophic, and the force is nearly impossible to stand against. A human body exposed to Category 5 winds would be lifted, thrown, and destroyed. That is the upper boundary of what our planet produces, 157 miles per hour at the low end of the Category 5 threshold. The most powerful tropical cyclone ever recorded on Earth, Typhoon Tip in 1979, generated sustained winds near 190 miles per hour. Hurricane Patricia in 2015 briefly sustained winds near 215 miles per hour. These are outliers. They represent the absolute ceiling of atmospheric violence on a planet with a surface, oceans, continents, and friction to slow things down. Saturn's equatorial winds blow at speeds approaching 1,100 miles per hour, with some measurements placing them higher depending on the assumed internal rotation rate. Check that number again. 1,100 miles per hour. Sustained. Not in a single gust. Not in a brief peak during a once-in-a-century storm, as a permanent, continuous structural feature of the planet's atmosphere. Every hour of every day, for as long as we have been able to measure them, the winds at Saturn's equator have been screaming eastward at speeds that make the most violent weather on Earth look like a light afternoon breeze. To put this in context that the human mind can actually process, 1,100 miles per hour is roughly 1.5 times the speed of sound at sea level on Earth. A commercial jet aircraft cruises at around 575 miles per hour. Saturn's equatorial wind would overtake a Boeing 747, pass it, and leave it behind as though it were standing still. If you placed a physical object in that wind stream, assuming the object could survive the atmospheric composition and temperature, the aerodynamic forces would tear apart any structure human engineering has ever produced. We have no materials rated for sustained exposure to wind loads at that velocity. Nothing we have built, Nothing we have designed, nothing we have even theorized about building could survive in Saturn's equatorial jet stream for more than a few seconds. And here is the detail that makes this genuinely unsettling. Jupiter, the planet everyone assumes is the atmospheric monster of the solar system, has equatorial winds of roughly 270 miles per hour. That is fast. That is dangerous. That is more than enough to destroy anything we could send into the atmosphere. But it is roughly 1/4 of what Saturn produces at the same latitude. 1/4. The planet that everyone fears for its atmospheric violence has equatorial winds 4 times slower than the planet people put on posters. This is not a disputed measurement. This is not a preliminary finding waiting for confirmation. Voyager 1 and Voyager 2 both measured Saturn's wind speeds during their flybys in 1980 and 1981. The Cassini spacecraft refined those measurements over 13 years of continuous observation from 2004 to 2017. The numbers are consistent across multiple instruments, multiple missions, and multiple decades. Saturn's equatorial jet stream is the fastest sustained wind system on any planet in the solar system. It has held that distinction for as long as we have been capable of measuring it, and it is not close. The natural question is why? Why would Saturn, a planet smaller and less massive than Jupiter, produce winds so dramatically faster? The answer lies in a combination of factors that are individually understandable but collectively produce a result that atmospheric scientists did not fully predict before direct measurement confirmed it. The first factor is rotation. Saturn completes a full rotation in approximately 10 hours and 33 minutes. That is fast. Jupiter rotates in about 9 hours and 56 minutes, which is slightly faster. Both planets spin so rapidly that their equatorial regions bulge outward significantly, giving both worlds an oblate shape that is visible even in amateur telescope images, but Saturn is less dense than Jupiter. Significantly less dense. Saturn's average density is approximately 0.687 grams per cubic centimeter. That makes Saturn the least dense planet in the solar system. It is, famously, less dense than water. If you could find an ocean large enough, Saturn would float. That comparison is scientifically imprecise, because Saturn's internal pressures would not remain stable in such a scenario, but the density figure is real, and its consequences are profound. Lower density means the atmosphere is puffier, more extended, and less gravitationally compressed at any given altitude compared to Jupiter. When you combine rapid rotation with a deep, low-density atmosphere, you get a planet where the Coriolis effect, the rotational force that deflects moving air masses, operates across a much wider vertical and horizontal range. The jet streams that form under these conditions are broader, deeper, and faster than what a denser atmosphere would produce under the same rotational speed. The second factor is internal heat. Both Jupiter and Saturn radiate significantly more energy than they receive from the Sun. Jupiter emits roughly 1.7 times the energy it absorbs. Saturn emits approximately 2.5 times the energy it absorbs. That ratio is higher for Saturn, and the source of that excess heat is itself a mystery that scientists have spent decades trying to resolve. The leading hypothesis involves helium rain. Deep inside Saturn, at pressures where hydrogen exists as a metallic liquid, helium becomes immiscible, meaning it separates out of the hydrogen mixture the way oil separates from water. Droplets of helium form and rain downward through the metallic hydrogen layer, converting gravitational potential energy into thermal energy as they fall. This process releases heat from the planet's interior continuously, driving convective currents that power the atmospheric circulation above. The result is a planet that is being heated from below by a mechanism that has no precise equivalent on Jupiter. Jupiter also has internal heat, but its higher gravity and different internal structure mean the convective dynamics operate differently. Saturn's interior heat source drives atmospheric circulation patterns that are in some ways more energetic than Jupiter's, despite Saturn receiving less sunlight and possessing less total mass. The winds are the most visible product of that internal engine, but they are not the only one. The storms are the next layer of the lie. When most people think of storms on gas giants, they think of Jupiter's great red spot. It is the reference point, the archetype, the visual shorthand for planetary weather at its most extreme, and it is genuinely extraordinary, a storm system larger than Earth that has persisted for centuries. But Saturn has something that, in certain respects, is even more remarkable, and almost nobody has heard of it. At Saturn's North Pole, there is a storm. It is shaped like a hexagon, not approximately, not vaguely, not in the way that a cloud formation might loosely resemble a geometric shape if you squint at it from the right angle. Saturn's North Polar hexagon is a sharply defined, six-sided jet stream pattern with straight edges and distinct vertices that has maintained its geometric precision for at least 4 decades of continuous observation. Voyager first imaged it in 1981. Cassini studied it in extraordinary detail from 2004 to 2017. In all that time, the hexagon did not break apart, did not drift, did not lose its shape. It rotated with the planet, locked to Saturn's internal rotation period, sitting over the North Pole like a crown made of wind. Each side of the hexagon spans roughly 8,600 miles. The entire structure is approximately 18,600 miles across. Earth's diameter is roughly 7,918 miles. You could fit the entire Earth inside the hexagon and have room left over on every side. The jet stream that forms the hexagon's walls moves at approximately 220 miles per hour. Inside the hexagon, at the very center of the pole, sits a separate vortex, a hurricane-like eye wall with winds exceeding 330 miles per hour and a diameter of roughly 1,250 miles. That central vortex alone is larger than many of Earth's most powerful storm systems. Nothing like this exists on Jupiter. Nothing like this exists anywhere else in the solar system. Nothing like this exists in any atmospheric model that was published before Voyager first photographed it. The hexagonal shape was so unexpected, so geometrically precise, so unlike anything planetary scientists had ever seen, that it took years of analysis before a plausible formation mechanism was even proposed. The current understanding is that the hexagon is a standing wave pattern created by the interaction between Saturn's polar jet stream and the surrounding atmospheric circulation. Laboratory experiments using rotating fluid tanks have successfully reproduced hexagonal and other polygonal flow patterns under specific conditions of rotation speed and fluid depth. The physics is comprehensible, but the fact that Saturn maintains this pattern at planetary scale with mechanical precision for decades without interruption speaks to an atmospheric system that is deeply structured, enormously energetic, and fundamentally different from what Jupiter produces. Jupiter's great red spot is chaotic. It is a turbulent vortex embedded in a turbulent atmosphere, maintained by the energy of the surrounding flow, but constantly changing shape, size, and internal structure. It has been shrinking for over a century. Its long-term survival is not guaranteed. Saturn's hexagon is the opposite. It is order imposed on chaos at a scale that makes the great red spot look impermanent. It is a geometric cage made of wind, sitting over a pole, rotating in lockstep with the planet's interior, and showing no sign of weakening or dissolution. And the hexagon is not the only polar feature Cassini discovered. Saturn's south pole hosts its own massive vortex, a towering cyclone with a clearly defined eye wall rising more than 40 miles above the surrounding cloud deck. The eye wall structure resembles a terrestrial hurricane, but on a scale that dwarfs anything Earth could produce. Warm air rises inside the eye, creating a column of descending clear air at the center, exactly like the eye of a hurricane. But this storm does not form over warm ocean water and dissipate when it hits land. It has no ocean. It has no land. It sits over a pole on a planet with no surface, powered by internal heat, and it does not stop. Jupiter has polar storms too. The Juno spacecraft discovered clusters of cyclones at both of Jupiter's poles, arranged in geometric patterns of their own. These are significant discoveries. But Jupiter's polar cyclones are more chaotic, less stable, and less geometrically precise than Saturn's hexagon. The comparison is not about which planet has more storms. Both planets are covered in storms. The comparison is about the character of the storms. Jupiter's atmosphere is turbulent and visually dramatic, but Saturn's atmosphere is structurally locked into patterns that suggest a deeper, more powerful organizing force beneath the visible cloud layer. This distinction matters because it tells us something about what is happening below what we can see. An atmosphere that produces geometric standing wave patterns at planetary scale is an atmosphere driven by internal dynamics of extraordinary consistency and power. The engine beneath Saturn's clouds is not sputtering and surging the way Jupiter's appears to. It is running at a constant, deeply embedded, almost mechanical level of output that imposes order on the chaos above it. And that level of structural energy is not something that weakens or pauses or dissipates. It is continuous, it is total, and it extends all the way down into regions where the atmosphere stops being a gas and starts being something else entirely. Now look at what Saturn shows you from the outside and compare it to what is actually happening. From a distance, through a telescope, or in a photograph, Saturn's atmosphere looks smooth. The cloud bands are soft. The color palette is muted, golds and creams and pale yellows. There are no obvious spots the size of planets, no dramatic red wounds in the southern hemisphere, no visually chaotic turbulent zones that scream danger from 400 million miles away. Saturn looks like a planet that has its affairs in order. A planet where the weather is settled, the atmosphere is calm, and the worst thing that could happen to you is a chilly breeze. That impression is the opposite of reality, not slightly off, not a minor mischaracterization. The opposite. Saturn's atmosphere is faster, deeper, more structurally violent, and more persistently extreme than Jupiter's in almost every category except visible chaos and radiation intensity. And the reason we do not perceive that danger is because of a simple photochemical fact. Saturn is farther from the Sun. Saturn orbits at roughly 9.5 astronomical units from the Sun, compared to Jupiter's 5.2. That means Saturn receives roughly 1/4 of the sunlight that Jupiter does. Less sunlight means less photochemical activity in the upper atmosphere. The complex chemical reactions that produce Jupiter's vivid colors, the reds and browns and oranges generated by sulfur compounds, phosphorus, and other trace molecules reacting under ultraviolet light, are muted on Saturn because there is simply less ultraviolet energy reaching the cloud tops. The result is an atmosphere that looks calmer because the chemistry that would make it look violent does not receive enough energy to fully express itself. Underneath those pale clouds, the same fundamental processes are occurring. The same convective cells, the same jet stream interactions, the same violent updrafts and downdrafts that drive storm formation. but the visual signature is dampened. Saturn's storms are there. They are enormous, they are powerful, but they do not advertise themselves the way Jupiter's do. You have to look harder. You have to measure more carefully. And even then, the scale of what you find can take years to fully appreciate. Consider the great storm of 2010 and 2011. In December of 2010, amateur astronomers began noticing a bright white spot forming in Saturn's northern hemisphere. Within weeks, the spot had expanded into a massive convective disturbance that eventually wrapped around the entire planet, creating a storm band that stretched more than 9,000 miles in latitude and encircled Saturn's full circumference. The storm's head, the leading convective cell, produced lightning flashes that were 10,000 times more powerful than any lightning on Earth. The energy released by the storm's convective activity generated a stratospheric vortex, a hot spot in the upper atmosphere that reached temperatures more than 150 degrees Fahrenheit higher than the surrounding air, making it one of the largest temperature anomalies ever observed on any planet. This was not a subtle event. This was a planetary-scale atmospheric explosion that lasted for nearly 9 months and affected Saturn's atmospheric chemistry for years afterward. The Cassini spacecraft documented every phase of it. The storm disrupted the normal banding pattern of Saturn's atmosphere, mixed material from deep below the visible cloud layer up into the stratosphere, and produced chemical signatures that had never been detected on Saturn before, including direct detection of water ice flung up from depths where the atmosphere is warm enough for liquid water to exist. These storms are called Great White Spots, and they appear on Saturn roughly once every 20 to 30 Earth years, corresponding approximately to one Saturnian year. They are seasonal, they are recurrent, and each time one appears, it produces atmospheric violence that exceeds anything Jupiter has generated in the same time period. Jupiter's Great Red Spot is persistent, but it is a stable vortex, a system in equilibrium. Saturn's Great White Spots are explosive outbursts, convective eruptions that release pent-up energy from deep in the atmosphere in catastrophic bursts that reshape the visible cloud layer globally. The difference is like comparing a continuously burning fire to a volcanic eruption. The fire is dangerous. It is always there. You can see it and plan around it. The eruption is dormant for years, invisible, undetectable, and then it releases in a single event that dwarfs the fire in every measurable dimension. Saturn's atmosphere stores energy and releases it explosively. Jupiter's atmosphere dissipates energy continuously. Both are hostile. But Saturn's pattern of dormancy, followed by catastrophic release, creates a hazard profile that is, in some ways, more dangerous, precisely because it is unpredictable and because the calm periods between eruptions reinforce the illusion that the planet is peaceful. And all of this sits on top of a deeper atmospheric structure that makes Saturn treacherous in a way that numbers alone do not fully capture. Saturn's atmosphere is deep, not just deep in the casual sense of having a lot of gas, deep in the structural sense of presenting an environment where the conditions change so gradually that there is no clear boundary between safe and lethal. On Jupiter, the transition from survivable atmospheric pressure to crushing depth happens relatively quickly. Jupiter's higher gravity means the pressure gradient is steep. You descend, the pressure builds fast, and within a relatively short vertical distance, you cross the threshold where any conceivable spacecraft or probe would be destroyed. That is dangerous, but it is honest danger. The gradient warns you. You feel the pressure building. The rate of change tells your instruments that you are running out of room. Saturn's lower gravity and lower density stretch the same pressure transition across a much wider vertical range. The atmosphere is extended. The pressure builds slowly, The temperature increases gradually. There are no sharp boundaries, no obvious markers that tell you this is the point of no return. You descend into Saturn, and the environment degrades so smoothly, so patiently, so incrementally, that by the time your instruments register conditions incompatible with survival, you have been falling for far longer and far deeper than you realized. The escape velocity at that depth may already exceed what your propulsion system can deliver. The atmospheric density may already be too thick for your engines to push against effectively. Saturn does not crush you the way Jupiter does. Saturn lulls you. It lets you fall gently, gradually, almost comfortably into conditions from which there is no return. And by the time you understand what has happened, the planet has already closed around you. This is the character of Saturn's danger, and it is fundamentally different from Jupiter's. Jupiter confronts you. Saturn absorbs you. Jupiter announces itself with radiation and visible chaos and a gravity well so steep that every instrument you carry tells you to turn back. Saturn welcomes you with gold-tinted clouds and a gentle pressure curve and the most beautiful ring system any world has ever worn. And then it does not let go. The Cassini mission revealed all of this. More than a decade of continuous data, thousands of orbits, millions of individual measurements. And the picture that emerged was not the Saturn of popular imagination. It was not the serene, golden world of the posters. It was a planet hiding extreme violence behind extreme beauty, a world where the atmospheric dynamics were more powerful than expected, the storms more explosive than predicted, the wind speeds more extreme than any model had anticipated, and the internal heat engine more active and more mysterious than Jupiter's. Cassini's grand finale, the series of orbits that took the spacecraft between Saturn's cloud tops and the innermost edge of the rings before the final plunge into the atmosphere, revealed one more detail that shifted the understanding of Saturn's danger. The gap between the rings and the atmosphere, a region that carried significant uncertainty in pre-mission models, turned out to be cleaner than worst-case predictions on some passes, but carried detectable fine dust particles on others, moving at orbital velocities. The particle environment varied from orbit to orbit, meaning the hazard was not just present, but unpredictable. Even in the space between Saturn's visible features, no pass through the ring plane could be assumed safe. The danger was intermittent, which in some ways made it harder to plan around than a consistent threat. Even Saturn's empty spaces are not empty. Even its silences are not safe. Even the gaps in its rings carry hazards that you cannot see until you are already inside them. That is the beautiful lie. Saturn does not look dangerous. Saturn does not sound dangerous. Saturn does not trigger the alarm bells that Jupiter triggers from 500 million miles away, and every single layer of that reassurance is false. The calm appearance hides the fastest winds. The muted colors mask explosive storm cycles. The smooth cloud bands conceal a pressure gradient designed to trap anything that enters. And the golden light reflecting off the ring system, the most beautiful sight in the solar system, illuminates a world whose hostility is exceeded only by its ability to hide that hostility from everything looking at it. Cassini did not arrive at Saturn expecting to be surprised. The mission was one of the most thoroughly planned in the history of planetary exploration. Scientists had data from Pioneer 11's flyby in 1979 and from both Voyager encounters in the early 1980s. They had ground-based telescope observations spanning decades. They had atmospheric models, gravitational models, ring structure models, and magnetospheric models that had been refined over 20 years of preparation. By the time Cassini entered orbit around Saturn on the final night of June 2004, the scientific community believed it had a solid working understanding of the planet. Saturn was expected to confirm and refine what was already known. Instead, It systematically dismantled one assumption after another. One of the earliest and most fundamental surprises involved something that should have been simple: Saturn's rotation period. For Jupiter, determining the rotation rate was straightforward. Jupiter's magnetic field is tilted relative to its rotation axis by roughly 10 degrees. That tilt causes the magnetic field to wobble as the planet spins, producing periodic radio emissions that can be timed with precision. The period of those emissions gives you the rotation rate of the planet's deep interior. Jupiter's internal rotation period is 9 hours, 55 minutes, and roughly 30 seconds. The number is clean, consistent, and has been confirmed by multiple spacecraft across multiple decades. Saturn should have worked the same way. Voyager measured Saturn's kilometric radio emissions and derived a rotation period of 10 hours, 39 minutes, and 24 seconds. That number was published, accepted, and used as the baseline for atmospheric wind speed calculations for over 2 decades. Then Cassini arrived and measured the same radio emissions. The period had changed. Not by a trivial amount, by roughly 6 minutes. The radio period Cassini measured was approximately 10 hours, 45 minutes, and 45 seconds. A planet does not change its internal rotation rate by 6 minutes over 20 years. The deep interior of a gas giant is far too massive and carries far too much angular momentum for its rotation to shift detectably on human timescales. The rotation period itself had not changed. What had changed was the radio emission pattern, and that meant the emissions were not directly tied to the internal rotation the way Jupiter's are. The reason traces back to Saturn's nearly perfect magnetic symmetry. Because Saturn's magnetic axis is aligned with its rotation axis to within less than 1 degree, the magnetic field does not wobble as the planet spins. There is no tilt to create the periodic signal that makes Jupiter's rotation so easy to measure. The radio emissions Voyager and Cassini detected were being modulated by something else, likely interactions between the magnetosphere, the solar wind, and the planet's upper atmosphere, rather than by the deep interior rotation itself. This meant that for years, every published wind speed measurement for Saturn had been calculated against a rotation baseline that was wrong. The equatorial wind speed of 1,100 miles per hour was derived by measuring cloud motion relative to the assumed internal rotation rate. If the true internal rotation is different from the assumed value, the wind speeds change. Depending on which rotation period you use, Saturn's equatorial winds could be somewhat slower or even faster than the canonical figure. The uncertainty does not eliminate the conclusion that Saturn's winds are dramatically faster than Jupiter's. Even the most conservative estimates place them far above anything Jupiter produces at comparable latitudes. But the fact that Saturn's true rotation period remained genuinely uncertain for over a decade after Cassini's arrival tells you something about the planet that no single wind speed number can capture. Saturn resists being known. Jupiter gives up its secrets readily. Its magnetic tilt hands you the rotation rate. Its visible storms hand you the wind speeds. Its radiation belts hand you the magnetic field intensity. Every major physical parameter of Jupiter is accessible through relatively direct measurement. Saturn forces you to work harder. It hides its rotation behind magnetic symmetry. It hides its storms behind muted photochemistry. It hides its winds behind clouds so smooth they look motionless. Every layer of understanding at Saturn has to be extracted through indirect methods, long-duration observation, and the kind of patient, sustained attention that most missions are not designed to provide. Cassini was designed to provide it. And the longer it stayed, the more the planet revealed. Saturn's orbital period is approximately 29.5 Earth years. That means a single Saturnian year spans nearly 3 decades. Cassini arrived during Saturn's northern winter, when the North Pole was tilted away from the Sun and shrouded in darkness. Over the course of the mission, Saturn moved through its northern spring equinox in 2009 and into northern summer. For the first time, a spacecraft watched an entire gas giant transition between seasons. The changes were far more dramatic than anyone anticipated. As sunlight began reaching the northern hemisphere, the atmospheric chemistry responded on a planetary scale. The blue-gray coloration that had characterized the northern polar region during winter gradually gave way to the golden hues typical of Saturn's sunlit latitudes. The hexagonal storm at the North Pole, which had been observed primarily in infrared during the dark winter years, became visible in reflected sunlight for the first time, revealing details of its internal structure and cloud-top textures that infrared imaging alone could not resolve. But the most significant seasonal discovery was what happened in the deeper atmosphere. The Great White Spot eruption of 2010, the planetary-scale convective storm described earlier, occurred during Saturn's northern spring. Scientists now believe these massive eruptions are seasonally triggered, linked to changes in solar heating that destabilize a convectively suppressed atmospheric layer. During the long Saturnian winter, the upper atmosphere cools and forms a stable cap over warmer air below. Energy from the interior accumulates beneath this cap for years, building pressure like steam under a sealed lid. When the seasonal change arrives and the cap weakens, the pent-up energy breaks through in an explosive convective event that wraps around the entire planet. This mechanism means that Saturn's most violent atmospheric events are tied to a clock that ticks once every 30 years. The storms are not random. They are quasi-periodic, building through decades of silent energy accumulation and then releasing in catastrophic bursts that last for months. The interval between eruptions is long enough that no single human mission, unless it lasts as long as Cassini did, would be present to witness one. A spacecraft arriving during the quiet decades between eruptions would see a planet that appears atmospherically calm. It would measure modest storm activity. It would record smooth cloud bands and gentle wind variations. And it would have no indication that the atmosphere is a loaded weapon, counting down to an eruption powerful enough to reshape the visible cloud layer from pole to pole. Jupiter does not behave this way. Jupiter's storms are continuous. The Great Red Spot has been raging for centuries. The atmospheric turbulence is persistent and visible at all times. There is no seasonal suppression cycle. There is no decades-long accumulation of energy followed by explosive release. Jupiter's atmospheric violence is honest. It is always present. It is always visible. You never approach Jupiter during a quiet period and mistake it for a calm planet, because Jupiter does not have quiet periods. Saturn has quiet periods. And those quiet periods are when the planet is most dangerous to your assumptions. Because a quiet Saturn is not a calm Saturn. It is a Saturn that is building towards something. And when that something arrives, it exceeds anything Jupiter has produced in the same time frame. This was one of Cassini's most profound lessons. Saturn cannot be understood through a flyby. It cannot be understood through a single year of observation. It cannot be understood by applying the expectations formed at Jupiter and assuming they will transfer. Saturn operates on its own timescale, reveals its dangers on its own schedule, and punishes impatience with ignorance. Every mission that has ever visited Saturn and left quickly has come away with an incomplete picture that underestimates the planet's true hostility. Only Cassini stayed long enough to see the mask slip. And even Cassini, after 13 years, left behind a dataset so rich that scientists are still finding new hazards buried in the numbers more than 7 years after the mission ended. Now we go inside. Not alongside the atmosphere, not skimming the cloud tops, inside, into the depths, through the layers, past the point where hydrogen stops being a gas and starts being something no human being has ever touched. We are going to descend into Saturn and into Jupiter side by side, using the same physical framework, the same measurements, the same instruments, and see which planet actually kills you first. The answer is not the one you expect. Imagine you are falling, not toward the ground. There is no ground. You are falling into a planet that has no surface, no floor, no bottom that any instrument has ever detected. Below you is an atmosphere so deep that it transitions from gas to liquid to metallic fluid across a vertical distance greater than the diameter of the Earth. Above you, the opening you entered through is already closing, not physically but practically, because every second you fall, the energy required to climb back out increases, and the atmosphere around you thickens by a fraction so small you almost do not notice it. Almost. This is what it means to enter a gas giant. And the experience is fundamentally different depending on which gas giant you choose. Jupiter and Saturn are both worlds without surfaces. Both will kill anything that enters them. Both represent environments so far beyond human engineering capability that the comparison to any terrestrial experience is essentially meaningless. But the way they kill you, the speed, the sequence, the character of the destruction, is so different between the two planets that the comparison reveals something important about the nature of danger itself. Let us begin with Jupiter, because Jupiter is the planet people expect to be worse. And in the opening minutes of a descent, that expectation is correct. You approach Jupiter from orbit. Before you even reach the upper atmosphere, you are already dying. Jupiter's radiation belts begin well above the cloud tops, extending outward in a torus of trapped charged particles that surrounds the planet like an invisible shell of poison. The intensity depends on your orbital altitude and latitude, but at the distances relevant to atmospheric entry, the radiation dose accumulates rapidly. An unshielded human body would absorb a lethal dose within minutes. Even inside a heavily shielded spacecraft, the radiation penetrates. It damages electronics. It degrades sensors. It introduces noise into every instrument, trying to measure what is happening outside. You are under attack before the descent begins. Saturn does not do this. Saturn has a magnetic field, and it has radiation belts, but they are dramatically weaker than Jupiter's. Saturn's surface magnetic field strength is a small fraction of Jupiter's, weaker by roughly an order of magnitude or more depending on the latitude of comparison. The radiation environment around Saturn is correspondingly less intense. A spacecraft approaching Saturn for atmospheric entry would experience radiation levels that are manageable, survivable, almost unremarkable compared to what Jupiter delivers. Your instruments work. Your shielding holds. Your sensors give you clean data. Everything about the approach feels controlled, routine, safe. That feeling is the first lie. Now, you enter Jupiter's atmosphere. The transition from space to gas is not a sharp line. There is no wall of air. The atmosphere begins as a thin haze of hydrogen and helium molecules, so sparse that the difference between being in space and being in atmosphere is almost undetectable. But on Jupiter, the density increases quickly. The planet's gravity is 2.5 times Earth's. That gravitational acceleration pulls the atmosphere tight against the planet, compressing the lower layers and creating a steep pressure gradient. Within the first 100 miles of descent, you are already encountering significant atmospheric resistance. The temperature rises, the pressure builds, the experience is aggressive. Jupiter grabs you and squeezes. The Galileo probe, the only human-made object ever to enter Jupiter's atmosphere, survived for 57 minutes after deploying its parachute. In that time, It descended roughly 95 miles into the atmosphere. The temperature rose to over 300 degrees Fahrenheit. The pressure reached approximately 23 times Earth's sea level atmospheric pressure. At that point, the probe stopped transmitting. Not because it was designed to stop, because the environment destroyed it. The heat warped its components. The pressure crushed its housing. The signal died, and the probe continued falling, melting, compressing, and eventually dissolving into the hydrogen sea below. 57 minutes, 95 miles. Dead. Now, enter Saturn. The upper atmosphere is cold, colder than Jupiter's. Saturn is farther from the Sun, and the cloud tops sit at temperatures approximately -270 to -300 degrees Fahrenheit, depending on altitude. The haze is thin. The hydrogen and helium are sparse. You begin to fall, and the first thing you notice is how gentle it feels. The gravity at Saturn's cloud tops is roughly similar to Earth's, approximately 1.06 times the gravitational acceleration you would feel standing on the surface of our planet. That is dramatically less than Jupiter's 2.5. Your descent is slower. The atmosphere resists your fall less aggressively. The pressure builds, but it builds at a rate that feels almost leisurely compared to the rapid squeeze of Jupiter's upper layers. For the first several minutes, nothing seems dangerous at all. The cold is extreme, but the pressure is manageable. The winds, if you have entered near the equator, are catastrophic, but if your descent trajectory avoids the equatorial jet stream, the wind shear in the upper atmosphere is less violent than what you would encounter at the same altitude on Jupiter. Your instruments are functioning. Your structure is intact. The data coming in is clean. Everything is fine. This is where Saturn begins to diverge from Jupiter in a way that redefines what dangerous means. On Jupiter, the steep pressure gradient means you reach the critical thresholds quickly. Within an hour, you are at pressures that destroy spacecraft. Within 2 to 3 hours, depending on your descent rate, you reach the region where hydrogen transitions from a molecular gas to a dense, supercritical fluid. There is no sharp boundary, no surface you splash into. The gas simply becomes denser and denser until it behaves more like a liquid than a gas, and you are embedded in it, unable to move, unable to float, unable to do anything except be carried deeper by the convective currents of a fluid that is simultaneously hotter than the surface of some stars and denser than any ocean on Earth. Jupiter kills you fast. The timeline from entry to destruction is measured in hours. The process is brutal, rapid, and unmistakable. At every stage, your instruments are screaming warnings. The pressure curve is steep. The temperature curve is steep. The message is clear: get out or die. Saturn's message is different. Saturn's message is almost nothing for a very long time, and then everything at once when it is too late. Because Saturn's gravity is lower and its atmosphere is less dense, the pressure gradient is shallower. The distance you must fall to reach the same pressure levels you encounter on Jupiter is significantly greater. On Jupiter, you reach 10 times Earth's atmospheric pressure within roughly 200 miles of descent. On Saturn, reaching the same pressure requires falling more than twice as far. The atmosphere extends, the layers stretch. The descent that felt manageable in the first few minutes continues to feel manageable for tens of minutes, then for an hour, then for longer. The temperature is rising, but slowly. The pressure is building, but gradually. The atmosphere around you is thickening, but the rate of change is so gentle that the difference between 1 minute and the next is barely detectable. There is no moment where the environment suddenly declares itself lethal. There is no sharp transition. There is only a smooth, continuous, patient curve that carries you deeper and deeper into conditions that are incrementally more hostile without ever crossing a threshold dramatic enough to trigger the alarm response that Jupiter triggers almost immediately. And this is the trap. Because while the pressure gradient is shallower, the destination is the same. Both planets ultimately compress hydrogen into a metallic state at pressures exceeding 1 million times Earth's sea level atmosphere. Both planets reach temperatures of tens of thousands of degrees in their deep interiors. Both planets have cores, probably rocky and metallic, sitting at the center under conditions so extreme that the materials there exist in states not found naturally anywhere else in the solar system. The endpoint is identical. The journey is different. Jupiter rushes you toward that endpoint. You know you are doomed from the first hour. Saturn walks you there, slowly, patiently, through an atmospheric layer so deep and so gradual that your perception of danger never catches up to the reality of your situation. By the time the pressure has risen to levels that compromise your structural integrity, you have been falling for so long, through so much atmosphere, that the energy required to reverse your descent and climb back out exceeds anything your propulsion system can deliver. You are trapped, not because Saturn grabbed you violently, but because it let you drift until the mathematics of escape became impossible. The chemistry of what surrounds you during this descent is another dimension of the comparison that separates the two planets in ways the pressure numbers alone do not capture. On both Jupiter and Saturn, the uppermost cloud layer is composed of ammonia ice crystals. These form at altitudes where the temperature drops below the condensation point of ammonia, roughly -200 degrees Fahrenheit. On Jupiter, this layer sits at a well-defined altitude and is clearly visible as the bright white zones between the darker brown and orange belts. On Saturn, the ammonia ice layer is also present, but it sits beneath an additional layer of haze, a thin fog of hydrocarbon particles produced by photochemical reactions in the upper atmosphere. This haze is what gives Saturn its smooth, muted appearance. It acts as a filter, softening the visual contrast between cloud bands and obscuring the ammonia ice crystals below. You descend through this haze first, and it tells you nothing. It is thin. It is quiet. It is almost featureless. It is the visual equivalent of a whisper in a language you do not speak. Below the ammonia ice layer, on both planets, lies a second cloud deck, composed of ammonium hydrosulfide, a compound that forms when ammonia reacts with hydrogen sulfide at slightly higher temperatures and pressures. This layer is darker, denser, and chemically more aggressive than the ammonia ice above. On Jupiter, it contributes to the brown and orange coloration of the belts. On Saturn, it sits deeper in the atmosphere because Saturn's lower gravity stretches the vertical distance between cloud layers. The journey from the ammonia ice deck to the ammonium hydrosulfide deck is longer on Saturn. The time spent between layers, falling through a region of relatively clear hydrogen and helium atmosphere with no major cloud features to provide visual reference points, is disorienting. You are falling through an atmosphere with no landmarks, no horizon, no up or down, except what your instruments tell you. The sameness of the environment is itself a hazard, because it erodes your situational awareness and makes the passage of depth feel meaningless until it is not. Below the ammonium hydrosulfide layer lies the deepest cloud deck visible to remote sensing, the water cloud layer. This is where the atmospheric story begins to diverge between the two planets in a way that directly affects survival. On Jupiter, the water cloud layer is relatively well constrained. It sits at a depth where the temperature has risen to roughly the freezing point of water, and the Galileo probe provided direct measurements of this region before it was destroyed. The water cloud layer on Jupiter is turbulent, thick with convective activity, and electrified. Lightning in Jupiter's atmosphere originates primarily in and around this layer, where updrafts and downdrafts cycle water droplets through a temperature gradient steep enough to generate charge separation. Jupiter's lightning is powerful by terrestrial standards. Individual flashes have been measured at energies roughly comparable to the most powerful lightning on Earth. Though some events exceed terrestrial lightning by significant margins, Saturn's water cloud layer sits deeper. The lower gravity and lower density stretch the atmosphere so that the temperature and pressure conditions required for water condensation occur at a greater depth below the visible cloud tops. This means the water cloud layer on Saturn is embedded in a region where the ambient pressure is already significantly higher than the corresponding layer on Jupiter. And Saturn's lightning, when it occurs, is not comparable to Jupiter's. It is categorically different. During the Great White Spot eruption of 2010, Cassini's radio and plasma wave science instrument detected lightning discharges from the storm that released energies roughly 10,000 times greater than a typical lightning strike on Earth. 10,000 times. These were not modest tropical thunderstorm flashes scaled up by planetary size. These were electrical events of a magnitude that has no terrestrial analogue. Each discharge released more energy than some of the most powerful explosions humanity has ever deliberately created. The strikes were so intense that they produced radio emissions detectable by Cassini from thousands of miles away, cutting through the background electromagnetic noise of the Saturnian system like a scream through silence. Imagine descending through Saturn's atmosphere and entering the water cloud layer during an active convective event. The lightning around you is not a threat you can compare to anything in your experience. A direct strike from one of these discharges would deliver more energy to your spacecraft than any design specification has ever accounted for. The electromagnetic pulse alone would overwhelm shielding systems designed for terrestrial or even Jovian lightning environments. And because the water cloud layer on Saturn sits deeper than on Jupiter, you encounter this hazard later in your descent, at a point where the pressure has already built to levels that constrain your maneuverability and where the energy cost of climbing back above the cloud layer is already prohibitive. Jupiter's lightning is dangerous. Saturn's lightning is an order of magnitude beyond dangerous, and it occurs in a region of the atmosphere that you reach only after falling long enough to believe the worst might already be behind you. The sequencing is what makes it lethal. On Jupiter, you encounter severe conditions almost immediately. The threats arrive in rapid succession: pressure, heat, turbulence, lightning, and each one reinforces the message that you are in a hostile environment. On Saturn, the threats are spaced out. You pass through the haze, quiet. You pass through the ammonia ice layer, calm. You fall through the gap between cloud layers, nothing. You reach the ammonium hydrosulfide deck, unpleasant but manageable. You begin to relax, and then you reach the water cloud layer, and Saturn releases everything it has been holding back. The thermal profile reinforces this pattern with lethal precision. On Jupiter, the temperature increases rapidly with depth. The steep gravitational compression of the atmosphere means that each mile of descent adds significant thermal energy. You feel the heat building almost immediately. Your thermal management systems engage early. The power required to reject heat from your spacecraft interior begins climbing within the first hour of descent. The timeline from comfortable to critical is short, and the rate of temperature increase gives you a clear, measurable countdown to thermal failure. Saturn's thermal profile is shallower. The temperature increases with depth, as it must in any atmosphere under gravitational compression, but the rate of increase per mile of descent is lower than on Jupiter. The first 1,000 miles of descent on Saturn produce a temperature increase that would take a much shorter descent to reach on Jupiter. Your thermal management systems are not stressed immediately. The heat builds, but it builds slowly enough that your systems cope. Your cooling capacity is not exceeded in the first hour or the second. The thermal margin looks adequate. The data looks manageable. But the margin is an illusion created by the gradient. The temperature is rising. It has not stopped rising. It will not stop rising. And because Saturn's atmosphere is deeper, the total descent distance before reaching any given temperature threshold is greater. Your cooling systems are running longer. They are rejecting heat into an environment that is itself getting hotter, which means their efficiency is declining even as the demand on them increases. On Jupiter, the thermal crisis arrives quickly, obviously, and with a steep curve that leaves no ambiguity. On Saturn, the thermal crisis arrives slowly, quietly, and on a curve so gentle that the moment where your cooling capacity is exceeded does not announce itself with a spike. It arrives as a gradual crossing, a point where the rate of heat rejection drops below the rate of heat absorption, and from that point forward, your internal temperature rises continuously, with no mechanism to reverse it. You do not notice the crossing when it happens. Your instruments register it as a trend change, not an alarm event. The numbers shift from stable to slowly increasing, and the rate of increase is modest enough that it does not trigger emergency thresholds. By the time the internal temperature reaches levels that degrade your systems, you have been falling for hours past the crossing point. The depth you have accumulated in those hours places you far below any altitude where escape is energetically possible. The thermal kill on Jupiter is abrupt enough to register as a crisis. The thermal kill on Saturn is measured in the quiet accumulation of degrees across a descent so long that the mathematics of heat transfer become the mathematics of inevitability. No alarm sounds, no threshold is crossed. In a single dramatic moment, the temperature simply rises and keeps rising and does not stop. This is the pattern that repeats at every level of the comparison. Every hazard on Saturn operates on a longer timescale, across a wider depth range, with a gentler gradient and with a later onset than the corresponding hazard on Jupiter. And in every case, the later onset and gentler gradient make the hazard more dangerous, not less, because they delay the recognition of danger past the point where the response to that recognition can change the outcome. There is a concept in engineering called the point of no return. It is the moment in a process where reversing course requires more resources than continuing forward. On Jupiter, the point of no return arrives early and announces itself loudly. On Saturn, the point of no return arrives later but arrives silently. You cross it without knowing. And by the time you realize what has happened, Saturn has already won. Now consider what you encounter during the longer descent. Saturn's winds do not weaken as you go deeper. In the upper atmosphere, the equatorial jet stream dominates at speeds already established as the fastest sustained winds on any planet in the solar system. But the wind systems extend deep into the atmosphere, far below the visible cloud layer. Cassini's gravity measurements, taken during the spacecraft's close orbits near the end of the mission, revealed that Saturn's jet streams penetrate to a depth of roughly 5,500 miles below the cloud tops. That is extraordinarily deep. The atmospheric circulation is not a shallow surface phenomenon. It is a deep structural feature of the planet, driven by the internal heat engine and maintained by the rotational dynamics of a rapidly spinning, low-density world. As you descend, you pass through multiple wind shear layers. The wind speed and direction change with altitude, creating zones where the forces on your spacecraft shift unpredictably. On Jupiter, these shear layers are also present, but Jupiter's steeper pressure gradient means you pass through them quickly. On Saturn, you spend more time in each shear zone. The forces accumulate. The structural fatigue on your spacecraft builds over a longer period. The vibrations, the oscillations, the constant adjustment of attitude and orientation required to survive in a shifting wind environment, all of it lasts longer because the descent lasts longer. And then there is the transition zone. Both Jupiter and Saturn have a region deep in their interiors where molecular hydrogen, the familiar gas that fills the upper atmosphere, gradually transitions into metallic hydrogen, a state of matter where hydrogen is compressed so densely that the electrons are stripped from their atoms and flow freely, making the material behave like a liquid metal. This transition does not happen at a sharp boundary. It occurs across a broad zone where the properties of the material change continuously from gas-like to liquid-like to metallic. On Jupiter, this transition zone begins at roughly 10,000 to 12,000 miles below the cloud tops. On Saturn, it begins deeper at roughly 18,000 to 20,000 miles below the cloud tops. The difference is significant. Saturn's transition zone is both deeper and more extended than Jupiter's, meaning the region of ambiguous material properties, where the hydrogen is neither fully molecular nor fully metallic, is wider on Saturn than on Jupiter. This matters because the transition zone is one of the most physically hostile regions inside either planet. The temperatures in this zone reach thousands of degrees. The pressures exceed hundreds of thousands of atmospheres. The material surrounding you is a supercritical fluid with properties that shift along gradients no terrestrial laboratory can replicate. The electrical conductivity increases as you descend, meaning the material around you begins to carry currents, generate magnetic fields, and interact with your spacecraft in ways that go far beyond simple pressure and heat. You are not just being crushed. You are being immersed in a conducting fluid that generates its own electromagnetic environment. On Saturn, you spend more time in this transition zone because the zone is wider. The extended depth range means a longer exposure to conditions where the physics of your environment is changing in ways that even the best models cannot fully predict. Jupiter's transition zone is brutal but compact. Saturn's is drawn out, a slow submersion into a state of matter that has no equivalent in ordinary human experience. And there is an additional factor that applies specifically to Saturn's transition zone that does not have the same significance on Jupiter. Saturn's internal heat source, the helium rain process described earlier, operates precisely in the region where molecular hydrogen transitions to metallic hydrogen. The immiscibility of helium in metallic hydrogen is what causes the helium droplets to form and fall. This means that inside the transition zone on Saturn, you are not only being subjected to extreme pressure, extreme temperature, and exposure to a metallic fluid, you are also in the middle of an active precipitation system where droplets of liquid helium are falling through the surrounding medium, releasing gravitational energy as thermal output. The environment is raining metal. Around you, through you, in a zone where the temperature is already thousands of degrees and the pressure is already hundreds of thousands of atmospheres. And this rain is one of the primary energy sources powering the atmospheric violence above you, the winds, the hexagonal storm, the explosive white spot eruptions. You are inside the engine. You are inside the mechanism that drives everything that makes Saturn dangerous, and it is still running. Jupiter has its own internal heat mechanisms, but the helium rain process is far less significant on Jupiter than on Saturn. Jupiter's greater mass and higher internal temperatures mean that helium remains more soluble in the metallic hydrogen layer, and the separation process is less pronounced. Saturn's cooler interior and lower pressures allow the helium rain process to operate more vigorously. This is one of the reasons Saturn emits proportionally more excess heat than Jupiter, despite being smaller and less massive. The engine is working harder on Saturn. The energy being released from the interior is, relative to the planet's size, more intense. Now step back from the technical details and look at the shape of the two experiences side by side. Jupiter grabs you at the door. Radiation before you arrive. Violent atmospheric compression within the first hour, a steep pressure gradient that announces lethal conditions quickly and clearly. A rapid descent through layers of increasing hostility, each one worse than the last, each one flagged by instruments screaming at unmistakable volume, a death that is fast, violent, and honest. You know what killed you. You knew it was coming. You had minutes to hours of warning, and none of it mattered because the force was too great to escape. Saturn lets you in. No radiation assault at the door. A gentle upper atmosphere, a pressure gradient so shallow that the first hour of descent feels survivable. Conditions that deteriorate so gradually that there is no single moment of alarm, no red line crossed with dramatic warning signals, no instrument reading that shifts from safe to lethal in a single jump. Instead, a patient, continuous tightening of the noose, so slow that by the time you feel it, the slack is already gone. A point of no return that passes without announcement. A descent that extends for hours longer than Jupiter's, through layers of increasing wind shear, through a broader and more hostile transition zone, into a metallic hydrogen interior powered by an active helium rain process that Jupiter does not share to the same degree. A death that is slower, quieter, and more thorough. Not because Saturn is a more powerful planet, because Saturn is a more patient one. There is one more comparison that must be made before we leave the interior, and it involves the magnetic fields. Jupiter's magnetic field is the most powerful of any planet in the solar system. Its dipole magnetic moment is roughly 20,000 times Earth's, producing surface field strengths at the cloud tops roughly 10 to 20 times stronger than what we experience on the ground. The field extends outward to create a magnetosphere so vast that it reaches beyond the orbit of Saturn. Jupiter's magnetic field is one of the primary sources of its radiation environment, trapping charged particles and accelerating them to energies that make the space around Jupiter one of the most hostile environments in the solar system. Saturn's magnetic field is weaker. Its magnetic moment is roughly 600 times Earth's, though the surface field strength at the cloud tops is comparable to Earth's own magnetic field, far weaker than what Jupiter produces. That is still powerful by terrestrial standards, but it is a fraction of Jupiter's. The magnetosphere is smaller, the radiation belts are less intense. On the surface, this looks like a clear point in Jupiter's favor on the danger scale. Jupiter's magnetic field is, obviously, measurably, overwhelmingly more dangerous than Saturn's. But magnetic fields do not only create radiation belts, they also interact with the internal dynamics of the planet. Inside both Jupiter and Saturn, the metallic hydrogen layer generates the magnetic field through a dynamo process, convective currents of electrically conducting fluid, creating self-sustaining magnetic loops. The strength of the surface field tells you something about the intensity of this process, but it does not tell you everything. Saturn's magnetic field has a peculiar property that Jupiter's does not share. It is almost perfectly aligned with the planet's rotation axis. The tilt between Saturn's magnetic axis and its rotational axis is less than 1 degree. Jupiter's magnetic field is tilted by roughly 10 degrees. Earth's is tilted by roughly 11 degrees. A perfectly aligned magnetic field is unusual. It suggests that the dynamo process generating the field operates under conditions of extraordinary symmetry, which in turn suggests that the internal circulation of the metallic hydrogen layer is more organized, more laminar, and more deeply embedded in the rotational structure of the planet than what exists inside Jupiter. This has implications for anything inside the planet. A more symmetric, more deeply rooted magnetic field interacts with the surrounding, conducting fluid in a more uniform way. The forces it exerts on material moving through the transition zone are more consistent. The electromagnetic environment inside Saturn's deep atmosphere is not chaotic the way Jupiter's is. It is structured, ordered, persistent. Like everything else about Saturn, it presents an environment that is less obviously violent, but more fundamentally inescapable. Jupiter's internal magnetic field is powerful and chaotic. Saturn's is weaker but geometrically precise. The difference mirrors the difference between their atmospheres. Jupiter is the louder, more visually dramatic planet. Saturn is the quieter, more structurally organized one. And in both cases, the quieter version turns out to be the one that traps you more effectively. The sum of all these comparisons produces a picture that does not fit neatly onto a simple ranking scale. Jupiter wins in radiation. Jupiter wins in raw magnetic field intensity. Jupiter wins in the speed of the kill. But Saturn wins in wind speed. Saturn wins in storm persistence and geometric organization. Saturn wins in the depth and duration of the descent. Saturn wins in the subtlety of the pressure gradient. Saturn wins in the breadth of the transition zone. And Saturn wins decisively in the dimension that may matter most of all: deception. Jupiter cannot deceive you. It does not have the ability. Everything about Jupiter is visible, measurable, and screaming at you from the moment you approach. You fear Jupiter because Jupiter gives you every reason to fear it, immediately, obviously, and with overwhelming force. Saturn can deceive you, and does. It deceives you with beauty. It deceives you with a gentle approach. It deceives you with a pressure gradient that whispers instead of shouts. It deceives you with an upper atmosphere that feels survivable long past the point where survival is possible. And it deceives you with a visual identity so thoroughly associated with elegance and wonder that the very idea of Saturn being dangerous feels like a contradiction. It is not a contradiction. It is the point. Now we pull back to the full system. The rings, the moons, the orbital dynamics, the gravitational architecture of a world that hides its hostility in every layer, from the cloud tops to the core, from the inner ring edge to the outermost shepherd moon. And it asks the question that matters most. What does it mean that one of the most admired objects in the solar system is also one of the most underestimated? Pull back now. Leave the interior. Rise up through the metallic hydrogen, through the transition zone, through the helium rain, through the deep convective layers and the 1,000-mile-per-hour winds and the pale golden clouds that hide all of it. Rise above the cloud tops and keep going. Because Saturn's danger does not end at the edge of its atmosphere, it extends outward. It fills the space around the planet. It inhabits the rings, the moons, the gravitational architecture of a system so complex that 13 years of Cassini data were not enough to fully map its hazards. And every single one of those hazards shares the same fundamental property as the atmosphere below. It looks less dangerous than it is. Start with the rings. The rings are the reason Saturn is famous. They are the reason Saturn appears on book covers and classroom walls and desktop backgrounds. They are the reason the word beautiful attaches to Saturn before any other word, including dangerous. And they are a field of high-velocity shrapnel. Saturn's ring system extends from roughly 4,300 miles above the cloud tops to more than 48,000 miles outward. The total span from the innermost edge of the D ring to the outer boundary of the E ring covers roughly 240,000 miles from Saturn's center, a radial extent that exceeds the distance between the Earth and the Moon. The rings are extraordinarily thin relative to their width, in their thinnest regions as little as 30 feet thick, though the main rings typically measure a few hundred feet in vertical extent, creating a structure that is proportionally thinner than a sheet of paper scaled to the size of a football field. That thinness is part of what makes them so visually elegant. Seen edge-on, the rings virtually disappear. Seen from above or below, They spread across the sky in a luminous disk of ice and rock that catches sunlight and scatters it in patterns that have mesmerized every human being who has ever seen them through a telescope. The particles that make up the rings range in size, from grains smaller than sand to boulders larger than houses. The vast majority are water ice, mixed with smaller amounts of rocky material and trace organic compounds that give certain ring regions their subtle coloration. Each particle orbits Saturn independently, following its own Keplerian path at a speed determined by its distance from the planet. Particles in the inner rings orbit faster than particles in the outer rings. The orbital velocities are not gentle. Material in the B ring, one of the densest and most prominent ring structures, moves at roughly 44,000 miles per hour relative to the planet's center. Material in the outer A ring moves at roughly 37,000 miles per hour, 44,000 miles per hour. That is roughly 20 times the speed of a rifle bullet. A particle the size of a grain of sand, striking a spacecraft at that relative velocity, carries the kinetic energy of a small explosive charge. A particle the size of a marble carries enough energy to puncture metal plating. A particle the size of a basketball would destroy any spacecraft humanity has ever built. And the rings contain trillions upon trillions of these particles, distributed across a disk so wide that it would take light more than a second to cross from one edge to the other. Any object attempting to operate within Saturn's ring plane faces a continuous bombardment environment with no safe corridor, no predictable gaps, and no reliable way to avoid impacts at the velocities involved. During the final phase of the Cassini mission described earlier, the spacecraft passed through a region between the inner ring edge and the cloud tops that carried significant uncertainty about particle density. Even there, the spacecraft encountered fine dust particles at densities high enough to register on its instruments. The particle impacts were small, but they were continuous. Every pass through the ring plane was a calculated risk, and Cassini was one of the most carefully navigated spacecraft in the history of planetary exploration, guided by teams with over a decade of experience operating in the Saturnian system. Jupiter has a ring system too. Most people do not know this. Jupiter's rings are thin, dark, and composed primarily of fine dust ejected from the surfaces of small inner moons by micrometeorite impact. They are virtually invisible from Earth and were not discovered until Voyager 1 photographed them in 1979. Jupiter's rings pose a negligible hazard compared to Saturn's. The particle density is orders of magnitude lower. The composition is fine dust rather than macroscopic ice and rock. The total mass is trivial. Jupiter's rings are an afterthought, a footnote in the story of the planet. Saturn's rings are an entire chapter of hazard that Jupiter simply does not possess, and the rings are not static. They are dynamic. Saturn's dozens of small inner moons interact gravitationally with the ring particles, creating waves, gaps, density variations, and transient structures that shift over timescales ranging from hours to decades. The moonpan orbits within the Encke gap, a roughly 200-mile-wide division in the A ring, and its gravitational influence creates visible wave patterns in the ring material on either side. The moon Prometheus orbits just inside the F ring, the thin, kinked, braided ring at the outer edge of the main ring system, and its gravitational perturbations create channels, streamers, and clumps of material that change shape with every orbit. The F ring itself is one of the most dynamically active structures in the solar system, constantly being disrupted and reformed by the competing gravitational influences of Prometheus and its companion moon Pandora. This dynamic environment means that the ring hazard is not something you can map once and navigate around. Forever, the threat changes, the particle distribution shifts, dense clumps form and dissipate, Impact probabilities vary from orbit to orbit. A path that was safe during one pass might be significantly more dangerous during the next. Saturn's ring system is not a static obstacle. It is a living, evolving, gravitationally stirred debris field that actively reshuffles its hazards on timescales shorter than most mission planning cycles. Now, move outward to the moons. Saturn has more than 140 confirmed moons. Jupiter has roughly 95. Both systems are complex, but Saturn's moon system adds layers of danger that Jupiter's does not replicate. Begin with Titan. Saturn's largest moon is the only moon in the solar system with a dense atmosphere. The surface pressure on Titan is roughly 1.5 times Earth's sea level atmospheric pressure. The atmosphere is primarily nitrogen, with methane and ethane playing roles analogous to water on Earth. Lakes and seas of liquid methane and ethane sit on the surface. Rain falls from hydrocarbon clouds. Rivers carve channels through water ice bedrock that is as hard as granite at Titan's surface temperature of -290 degrees Fahrenheit. Titan sounds almost Earth-like when described in those terms. And that resemblance is part of why it captures the imagination. But Titan's chemistry is profoundly hostile to anything built for terrestrial conditions. The liquid methane that fills its lakes is a cryogenic fluid. Equipment designed for Earth temperatures would shatter on contact with Titan's surface. The organic haze that fills the upper atmosphere blocks nearly all visible sunlight, creating a surface environment dimmer than twilight on Earth. The complex organic chemistry occurring in Titan's atmosphere, called tholin production, generates a continuous rain of sticky organic compounds that coat everything on the surface in a dark, tar-like residue. Any lander operating on Titan would need to contend with cryogenic temperatures, hydrocarbon solvents, perpetual darkness, and a surface coated in organic sludge, all underneath an atmospheric pressure high enough to complicate every mechanical and thermal system aboard. The Huygens probe, carried to Titan by Cassini and released in January 2005, transmitted from the surface for approximately 72 minutes before contact was lost as Cassini moved beyond communication range. In that time, it transmitted images of a landscape that looked hauntingly like a dry riverbed on Earth, except the pebbles were made of water ice and the fluid that carved the channels was liquid methane. Huygens remains the most distant landing ever achieved by a human-made spacecraft. The data it returned reshaped our understanding of Titan, but it also confirmed that the Moon's environment is fundamentally incompatible with any prolonged human presence using current or near-future technology. Jupiter has no equivalent. Its largest moons are extraordinary in their own right. Europa's subsurface ocean is one of the most compelling targets in the search for extraterrestrial life. Ganymede is the largest moon in the solar system and the only moon with its own magnetosphere. Io's volcanism is unmatched. But none of Jupiter's moons presents the layered environmental hostility that Titan does. The combination of dense atmosphere, cryogenic surface chemistry, hydrocarbon precipitation, and organic surface contamination creates a hazard profile that is unique in the solar system. And it belongs to Saturn. Then there is Enceladus. This small moon, only 313 miles in diameter, would be unremarkable except for one extraordinary feature. Enceladus has a global subsurface ocean of liquid water, heated by tidal interactions with Saturn and kept liquid beneath a shell of ice, roughly 12 to 20 miles thick. At the Moon's south pole, fractures in the ice shell called tiger stripes vent plumes of water vapor, ice crystals, and organic compounds directly into space. Cassini flew through these plumes multiple times and detected molecular hydrogen, silica nanoparticles, and complex organic molecules, all consistent with hydrothermal activity at the ocean floor. The plumes of Enceladus feed material directly into Saturn's E-ring, the broad, diffuse ring that extends far beyond the main ring system. This means Saturn's outermost ring is being continuously resupplied by geological activity on one of its moons. The connection between the moon and the ring system creates a unique hazard. The E-ring particles are predominantly ice grains, less than 1 micrometer in size, but they extend across a vast volume of space and they are being continuously replenished. Any spacecraft operating in the outer Saturnian system must contend with this constant, low-level particle environment created by a moon venting its interior into orbit. Jupiter has nothing equivalent. Europa may have subsurface water, but it does not vent plumes into space at the same rate or with the same consistency. Io's volcanic emissions feed Jupiter's magnetosphere with sulfur and oxygen ions, but this creates a plasma environment rather than a particulate debris field. The mechanism by which Enceladus connects its internal ocean to Saturn's ring system is unique. It is a living geological process, feeding a planetary hazard in real time. Now consider the gravitational dynamics of the system as a whole. Saturn's moon system is not more chaotic than Jupiter's in every respect. Jupiter's 4 Galilean moons interact through a gravitational resonance called the Laplace resonance, which locks the orbital periods of Io, Europa, and Ganymede into a precise ratio and drives the tidal heating that powers Io's volcanism and Europa's subsurface ocean. That resonance is one of the most elegant and powerful gravitational interactions in the solar system. But Saturn's system has its own brand of gravitational complexity. The sheer number of moons, many of them small and irregularly shaped, creates a web of gravitational interactions that affects the ring system, the orbital stability of other moons, and the trajectory of anything trying to navigate through the system. Small moons, embedded within the rings, act as shepherds, clearing gaps and creating density waves. Mid-sized moons in orbits just beyond the rings exchange angular momentum with ring particles, slowly evolving the ring structure over time. Distant, irregular moons in retrograde orbits suggest a history of capture events, where Saturn's gravity snagged passing objects and imprisoned them in orbits that are often highly inclined and eccentric. For a spacecraft or hypothetical crewed mission operating in the Saturnian system, the navigation challenge is not just avoiding the rings. It is tracking the gravitational influences of dozens of moons, accounting for the perturbations they create, and planning trajectories through a dynamical environment that is more crowded and less predictable than Jupiter's in certain critical regions. This is the system-level picture of Saturn's danger. It is not a single threat. It is not a single overwhelming force like Jupiter's radiation or Jupiter's gravity. It is a layered, distributed, interconnected set of hazards that operate at every scale, from microscopic ring particles to moon-sized bodies venting their interiors into orbit. And every layer shares the same essential characteristic. It does not look as dangerous as it is. Now step all the way back. Leave the Saturnian system. Return to Earth. Return to the place where a child draws Saturn with crayons, adding a ring around a yellow circle and smiling because it is the prettiest planet. Return to the place where a student opens a textbook and sees Jupiter described as the king of the solar system, the most massive, the most powerful, the most dangerous. Return to the starting point of this story, where we asked a simple question: which planet is more dangerous? The answer is not simple. And that is the point. Jupiter is more dangerous in specific, measurable, unmistakable ways. Its radiation environment is lethal at distances that Saturn's is not. Its gravitational pull is stronger. Its magnetic field is more intense. If you define danger as the most immediately lethal single threat, Jupiter wins. No serious analysis would argue otherwise. Jupiter's radiation belts alone represent a hazard that Saturn cannot match. But danger is not only about the single most lethal threat. Danger is also about exposure, duration, deception, and the gap between what you expect and what you encounter. And in every one of those dimensions, Saturn is more dangerous than Jupiter. Saturn's winds are faster. Saturn's storms are more explosive and less predictable. Saturn's atmospheric descent is longer, more gradual, and more deceptive. Saturn's transition zone is broader and complicated by an active helium rain process. Saturn's ring system is a continuous high-velocity debris field with no equivalent at Jupiter. Saturn's moon Titan presents a layered environmental hostility that no Jovian moon replicates. Saturn's moon Enceladus feeds material into the ring system in real time, creating a dynamic particle environment that evolves continuously. And Saturn's appearance, the golden clouds, the geometric rings, the muted color palette, creates a psychological expectation of safety that is not just wrong, but inverted. That last point is not a soft argument. It is not a rhetorical flourish added for dramatic effect. It is a statement about how human beings and human-designed systems assess risk, and it has direct, practical consequences for planetary exploration. When NASA planned the Cassini mission, the spacecraft was designed primarily around the known hazards of the Saturnian system. But several of the most significant discoveries Cassini made, including the intensity of Saturn's atmospheric winds, the structure and persistence of the North Polar hexagon, the depth of the jet stream penetration, the activity of Enceladus's plumes, and the particle density in the gap between the rings and the atmosphere, were surprises. They were not predicted by pre-mission models. They were not accounted for in the original mission design. They were discovered because Cassini was there long enough and capable enough to find them. Each of those surprises represented a hazard that was more significant than expected. The particle environment in the ring gap was denser than models predicted. The plume activity on Enceladus was more vigorous and more chemically complex than anyone anticipated. The atmospheric dynamics were more extreme than pre-Cassini simulations suggested. In every case, the reality was more hostile than the expectation. And in every case, the expectation had been shaped, at least in part, by Saturn's visual reputation as the elegant, beautiful, well-behaved planet of the outer solar system. Jupiter does not create that kind of expectation gap. Jupiter's hostility is priced in. Every mission to Jupiter is designed from the first sketch with the assumption that the environment will be among the most lethal in the solar system. Radiation shielding is a primary design driver. Trajectory planning accounts for the intense gravitational field. Instrument selection is constrained by the need to survive in an environment that actively destroys electronics. The fear is built into the engineering from day one. Saturn gets less fear. Saturn gets more admiration. Saturn gets the aesthetic benefit of the doubt. And that benefit of the doubt, translated into mission design, into risk assessment, into the assumptions that guide every decision about how to approach and operate around the planet, creates a systematic underestimation of the hazards that is itself a form of danger. This is what the title of this story actually means. Saturn may be more dangerous than Jupiter, not because it is objectively worse in every category. It is not. But because the specific ways in which it is dangerous are precisely the ways that human beings are worst at recognizing, we are good at fearing the obvious. We are good at respecting the loud, the large, the visually dramatic. We are terrible at fearing the quiet, the beautiful, the gradual, and the hidden. Our risk perception is calibrated for lions, not for rivers with undertows, for red storms the size of planets, not for pressure gradients that whisper. Saturn exploits every blind spot in human threat assessment. It is quieter than Jupiter, so we assume it is calmer. It is more beautiful than Jupiter, so we assume it is gentler. Its radiation is weaker than Jupiter's, so we assume the environment is more forgiving. Its clouds are smoother than Jupiter's, so we assume the atmosphere is less violent. Every assumption is wrong. And every wrong assumption brings us closer to the kind of mistake that the vacuum of space does not forgive. There is a broader truth here that extends beyond planetary science. The universe does not label its dangers. It does not paint its most hostile environments in warning colors or attach sirens to its most lethal phenomena. Some of the most dangerous places in the cosmos are also the most beautiful. Neutron stars pulse with mesmerizing precision while radiating enough energy to sterilize entire solar systems. Black holes bend light into luminous rings while concealing a boundary from which nothing returns. Nebulae glow in colors so vivid they look painted while harboring temperatures and radiation levels that would obliterate anything within them. Beauty and danger are not opposites in the universe. They are frequently the same thing viewed from different distances. Saturn is the clearest example of this principle in our own solar system. It is a world that has been admired, studied, and celebrated for 4 centuries, and in all that time, its most fundamental characteristic has been hiding in plain sight. It is hostile. It is extreme. It is dangerous in ways that are measurable, specific, and in several critical dimensions, greater than Jupiter's. And it has been concealing all of it behind the single most beautiful planetary image the human species has ever known. The child who draws Saturn with crayons is not wrong. Saturn is beautiful. The rings are real. The golden glow is real. The geometric elegance is real. But beauty is not safety. Elegance is not gentleness. And the most dangerous thing about Saturn, the thing that makes it arguably more threatening than the planet everyone already fears, is that it convinced the entire world it was something it is not. Jupiter roars. You hear it and you run. Saturn hums. You hear it and you come closer. And by the time you realize what you are hearing, you are already inside, falling through an atmosphere that has no floor, wrapped in winds that exceed anything Jupiter produces. Descending toward a metallic ocean powered by helium rain, surrounded by a ring system that fires ice and rock at orbital velocities, orbited by moons that vent their interiors into space, and watched over by a hexagonal storm the size of a planet that has not blinked in 40 years. That is Saturn. That is the planet you never feared. And now you know why you should have.